Welcome back, AutoCAD programming enthusiasts. All right, for the last video in this series, I'm just going to go through and explain all the functions in Architectural Windows. As I've shown before, I have it broken up into two files: Architectural Windows Support Functions and Architectural Windows. So, in any case, I have made this series of videos for people who have some experience programming, probably a little bit of experience programming in AutoLisp in AutoCAD. And so my experience is that you learn the fastest by examining a program that is slightly above your skill level. And so uh, after showing you all I've shown and demonstrated all I've demonstrated, I think to round this all out, it'd be silly not to go function by function to explain to you the code. And so I'm going to start with the support functions first. If you hear something in the background, it's my girlfriend and her daughter watching some movie on YouTube. But they're keeping it low, and hopefully her daughter won't make too much noise. But in any case, here we go. All right, now the program needs to toggle the object snaps on and off, because when a program is drawing, it always draws without snaps on, because it is assigning exact coordinates. It'll never say, I want you to draw to this point on the end of this line, or the midpoint of that line, or the center of this circle. It's always going to give an exact coordinate. But if the object snaps are on, it could accidentally snap to a point uh, that, if you have object snaps on. Now, one way to turn off object snaps is just to set the AutoCAD variable OS mode, object snap mode, to 0. Okay? And when the program is done drawing, it has to uh, change the object snap mode back to whatever it was uh, before the program started running. And it does that with toggle snaps on. So the first thing that happens is it saves the value of OS mode, and then it sets the value of OS mode to 0, turning object snaps off. And then toggle snaps on just sets the OS mode system variable, AutoCAD variable rather, to the value that it was saved. Uh, I'm sorry, it's 9:40. I'm kind of tired. I'm going to step it up now. In any case, it sets it back to the variable that was set by the toggle snaps off function. Okay, now the error routine is changed to a function that will toggle snaps back on if someone hits the escape key, all right, or control C's out of the function. And you want to do that just because you want the program to run cleanly. You don't want people to lose their running object snaps if they hit escape and uh, get out of the program, or if there's some other unexpected error. And so this defines the star error star function, which is the error routine. And then when it's time to unload the standard error routine at the end of the program running, it unloads it by setting star error star to nil. Now, this function here does exactly what it says. It gets the 3D world coordinate system points from a lightweight polyline. And it does so by calling these functions, which are below in the program. The first thing it does is it gets the two-dimensional entity coordinate system points from the lightweight polyline by calling this function, which will be below. And then it gets the entity coordinate system by running this function, get ECS transform matrix on the same polyline. And then what this does is it changes the format of the entity coordinate system points of the polyline to what I call four space format, where all the x coordinates are put together in a list, all the y coordinates are put together in a list, and then all the z coordinates are put together in a list, followed by a list of ones. And that is a format that creates a matrix that can be multiplied by another matrix, in this case, a transform matrix. And then once it has the four space entity coordinate system points, it gets the four space world coordinate system points by multiplying those four space 2D entity coordinate system points by the entity's coordinate system together. And then in order to get those same coordinates in three space format, which is just a list of vectors, 3D vectors, and the vectors themselves are just a list of three numbers, the x and y and z coordinates. This is run, and that is what is returned by the function. Now this here is just a very short function that draws lines between points in four space format. Ent to hand is a function that returns a handle given an entity name. A handle is a unique identifier for any entity that stays the same between AutoCAD sessions rather. Entity names do not. They are always changed from session to session, but so each entity has a handle, and that stays the same from session to session. Clear user input just gets a whole bunch of user input savings, and I'm sorry, that's what set user input does. I'm sorry. Clear input, clear user input records all these various user input settings and puts it into variable user input settings. It gets the object snap mode, the 3D object snap mode, UCS detect, the current layer, the @rec value. Uh, these are all AutoCAD system variables that could be changed during the program, and they need to be saved before they're cleared, put to zero. When they're put to zero, a lot of errors are avoided when the program goes to draw. And so once those are saved, it sets those variables all to zero. And then the exact same, the set user input does the exact opposite. It resets all these system variables to what they were before. Unique ID returns just that, a unique ID. And the way it does it is it draws a point at the origin, and then it gets the handle. That's the same function here as ent to hand, as you can see. I should have just used ent to hand. I don't know why I didn't do that. And so sometimes you need a unique ID. This program has what is in effect a database in it, and sometimes you need unique identifiers on entries. In this case, it's an entry. It's the indexes in the window dictionary to give each window dictionary a unique ID. Now, copy and place is used to copy entities, duplicating them without moving them. And all it does is it executes the copy command uh, and enters 00, enters the origin for both the to and the from. And here's the copy command. And what it does is it creates a marker with a point entity. And then it copies an entire selection set or an individual entity from point to point. And then what it does here is it returns a selection set of the new entities. The last function, evaluation, is always returned by AutoLisp to the calling function. In any case, continuing, this function gets all the entities from a marker entity. It's used in the copy function, which we use. Here's the get entities from marker function. And what it does is it takes the marker and it goes through the database with the entNext function. It says entNext. What happens here? Oh yeah, well it sets the current to the marker. Okay, and then it uses the entNext function to cycle through the entire database until it reaches the end, and it puts it all into a selection set with the SSAdd function. And if there's a filter, which is an entity type, and can get all the 3D solids, for example, or all the lines. And if there is an entity type specified, it will filter just for that entity. Then the marker itself is erased, and then the selection set is returned here. Now, spatial conflict solid, that's what you get when you do an intersection between two 3D solids. But this function does not modify the two solids that is passed. It copies the two solids that is passed, and then it does an intersection. And if there is no intersection, it returns nil. And if there is an intersection, it returns the entity name of the spatial conflict solid that was just created. We use that to test to see if a window is inside of a wall in the Architectural Windows program. Now, get 3D solid volume does just that. It gets the internal volume of a 3D solid object. That's used to figure out how thick walls are in the program. And it uses the VLAX get function. And what the VLAX get function is, it stands for Visual Lisp ActiveX-get. There is a massive number of functions and properties in the ActiveX interface for AutoCAD that is not available in regular AutoLisp, but they are available through the ActiveX extension with VLAX get and VLAX put. And first it gets the ActiveX entity name from the entity name in AutoLisp, and then it passes that, and then it asks for uh, the particular um, property that is desired. In this case, is volume, and it returns it. And the same thing happens with the get pline area function, which is also used to figure out wall thicknesses in the program. And it's VLAX get, the ActiveX entity name, and the area property. These are all properties that are available in the ActiveX uh, programming interface. And so here's the function I described above. It gets the 2D entity coordinate systems from a polyline. And it just cycles through it, and it gets all the dot pairs that start with a 10, which is a 3D point. There are others, and they're just discarded. It cycles through the entity DXF, which is returned by the entget function. Here's the function that turns a 3-space vector list into a 4-space vector matrix that can be multiplied by a transform matrix. And basically what it does is it creates 4 lists, and it goes through and it puts all the x coordinates into the first list, puts all the y coordinates into the second list here, puts all z coordinates into the third list, and then it just puts ones in that fourth list, and it returns a list of those lists. And that's how the 4-space vector matrix is created. And the 4SP to 3SP function does the exact opposite, and it uses the vector transpose function in order to do it, believe it or not. What it does is it reverses the list. It uses the CDR function to strip off the list of ones, and then the list is reversed again, and then the transpose of that is taken. So all the columns become rows, or rather all the rows become yeah, all the rows become columns. And so here is the matrix multiplication function, and what it does is it just implements the matrix multiplication algorithm that everybody learned in high school, hopefully. And it just goes through it in one at a time with 2 while loops. While the row counter is less than 0, it goes through all the columns. While the column counter is, greater than 0. The get ECS transform matrix does just that. It gets the entity coordinate system transform matrix from an entity. And how does it do that? Well, first thing it does, it gets the entity DXF with the entget command. And DXF code 210 is the z-axis of the entity coordinate system. And if the z-axis is 001, then that is just a world coordinate system. And so it sets the x-axis and y-axis axis to 100 and 010. But if it's not, that means the z-axis is not just straight up and down. And so you get the x-axis by crossing the world coordinate the z-axis value by the z-axis of the world coordinate system. And then it gets the y-axis by crossing the z-axis with the x-axis. And then it gets the elevation of the plane, the xy plane of the ECS transform matrix from the from value 38, what do they call it, DXF code 38 in the entity DXF. If it's not there, the elevation is 0. And then it just returns this matrix, which is defined by those two uh, entries in the DXF. There's the elevation, um, which is entity code, DXF code 38 of the entity DXF, and the z-axis, which is DXF code 210. And then it figures out uh, this matrix and returns it. This is explained in a video that I did on entity coordinate systems, and this is the result of the content of that video. The content of this function is explained in my video on entity coordinate systems. Now, the following are just basic vector functions. This is a vector cross product, and this is the definition that you should have learned in high school. Here's the vector length function, and this right here is just what is this, Pythagoras theorem? Square of the x, the square of the y, and the square of the z, square rooted. Yeah, that's Pythagoras theorem. This is a function that returns a unit vector, which is a vector of length 0 from any given vector, and all it does is it takes a vector and it divides it by its length right here. Sometimes I need a square function, and there is none in AutoLisp, so I just entered it right there. Now this row function returns the row of a matrix, which is just a list of lists. The column function does the same thing, except it has to pick out the nth value of each row, and it returns that in a list. What is MV dot? Oh, this is a this is a vector cross function for vectors which are longer or shorter than three values. That's all that is. That's what this is. It's basically a vector dot product. Here's a transpose function for a matrix. And as you can see, here's the vector add function. It just adds the x value of vector A and B together, and the y value and the z value, and then it returns it in a list. And here's the vector subtract function, which is almost the exact same thing. And here's the create dictionary function. This is the OLS code that's needed to create a dictionary in the AutoCAD database, as it turns out. Oh, do I have a vector? Oh, here's the vector dot product, where x is the two x values of the two different vectors are multiplied by each other, the same as with the y values and the z values. All right, sometimes you have a dictionary and you need to get a child dictionary, like when you have the window dictionary, you need to get a particular window dictionary. You need to get a particular window dictionary in the window dictionary. So what you do, you got that dictionary and you got the key of the child dictionary, and this is the code that you need to run in order to get the entity name of that child dictionary. This is just a function that prints a symbol list. This here is a function that returns a transform matrix for a rotation around the z-axis by a particular angle. And there's that familiar cos, negative sine, sine, cos, 2D rotation matrix. Sometimes you just need to return an x-coordinate of a vector, y-coordinate, or a z-coordinate. This here is returns a transformation matrix that just offsets by a particular vector. No rotation. This is just a translation or an offset. That's all that does. All right, what this here does is it creates a user coordinate system that is described by a transformation matrix. It's pretty simple. Now these are just functions that I use, commands that I use when drafting to move around the user coordinate system that I'm using to draw on. And this function moves the user coordinate system origin. This function returns to the world coordinate system. This moves to the user coordinate system of a particular entity. This goes back to the previous user coordinate system. This rotates the user coordinate system around the current x-axis by 90 degrees. This is the same thing for the y-axis and the z-axis. And this here, uh, that's actually not correct, but it allows you to move to a user coordinate system defined by 3 points. And these are the functions that are called by those commands. These are called by functions. I mean, these are functions that are called by these commands or by a program. Let's see. This here returns a transform matrix that I think I had that up here somewhere. That is a rotation around the z-axis by a particular angle. I think I had that up there. This draws a series of lines between 3D points. That's all that does. Now this here draws a 4 by n matrix given a 4 by n matrix and the lower left point. That's a function I used in that video that explained 4x4 transform matrices. And I'll be damned, that's it. Those are all the support functions. Now on to the main functions in Architectural Windows that call those functions. All right, so first thing that happens is if none of the support functions are loaded, they are loaded. That's what happens with this particular line. And these here just set some global variables. And this is the main program command dispatch loop. It toggles the snaps off. If the window frame layer or the window glass layer doesn't exist, they are created. The standard error routine is loaded. the user input variables are cleared out, and the main command dispatch loop is started here. And the possible subcommands are new window, adjust a window, modify, delete a window, or exit from the command. And so the user's asked for a keyword, and then if he asks for a new window, the add window function is run. If the user chooses the adjust option, the modify window function is run. If the user chooses the delete option, the delete window function is run. And if the user chooses the exit option, continue is set to nil, and then the loop is exited, and in preparation for the command to end, user input is set, the snaps are toggled back on, and the standard error routine is unloaded. This printsy function makes sure that there is nothing printed on the command line, or rather just a blank line is printed. Otherwise, the last returned value would be printed out. All right, and here's the add window function. Now, since some user input is necessary, snaps are toggled back on. And you can choose a corner of a window or choose a rectangle. And so if the user chooses rectangle, the user is then prompted to select a polyline rectangle. And if that entity was a polyline, then the create new window from rect in wall function is run, and that particular polyline entity name is passed to it. And then after the window is drawn, the user is asked if the source rectangle should be deleted. And if he says yes, then the rectangle is deleted. And otherwise, if the user does not choose the rectangle function, instead chooses indicates a point, then snaps are toggled back on, and this command pause, what this does is this allows the user to manually enter the opposite point of the rectangle. The rectangle command is started, and that point that the user input is entered, and then the user is allowed to indicate another point. The snaps are toggled back off, and then the create new window from rect and wall using that last entity is called, just like it was up here, but with the polyline rectangle that the user had selected. In the end, in either case, the create new window from rect and wall function is called. Now, modify window. First thing that happens is that the user is asked to select a particular window. And so then what happens is if the user chooses a window, that window entity, the window entity is used to search through the window dictionary, goes through every single window dictionary in the window dictionary to see if that entity is part of an existing window. And if it is, uh, what happens is it's the information is gotten from the window dictionary, and a user coordinate system is called up and created that aligns with that particular window dictionary. User input is then required, so uh, snaps are toggled back on, and then a loop is entered where uh, the adjust window function is called over and over again until the window is adjusted to the user's liking. And what happens in adjust window? A new window is created by changing some of the data of the old window, and the new window is substituted for the old window, and the old window and its dictionary is deleted, and the hole that it was in is filled up, and then a new hole is made for the new window, and the new Windows dictionary is added to the window dictionary. Now for delete window, it's much simpler. Same thing happens. A window entity is chosen, and this function here is called to see if it's part of one of the existing windows. And if it is, the that dictionary is identified in the window dictionary, and then it is deleted along with the window entities, and the user is told that the window is deleted. Otherwise, if that entity was not part of a window, the user is told that it's not an entity of a known window. And this function just simply gets all walls, and this is a function ssget, um, which creates an entity set of all entities on layer wall layer. Okay, this function create new window from rect and wall that was called from the other functions. It just takes a polyline rectangle and it cycles through each wall entity and sees if uh, that polyline rectangle lies along the side of a wall. The entity is copied in place, and each of those entities are extruded, and one direction and one in the other, and then those new 3D solids that are resulted are used to see if it's there's an intersection with a wall, and if there is, then it knows that that is the correct wall that's involved with this, that the rectangle is on. And once it knows that, it calls the draw window from rect function. It figures out what the wall thickness is using the rectangle areas and the window window hole volume, and it gets the wall thickness, and then this function, draw window from rect, which takes the polyline rectangle, the wall that it's on, and the wall thickness, and it draws it one way, and then it's tested to see if that window is inside the wall. What it does is it gets the glass entity from the window dictionary, and it uses that function, the what was it? That function that not the union, intersection. It takes an intersection of those two entities, and it sees if there is a solid with a non-zero volume, and if there is, that means that window is inside that wall. But if there's not, it's not inside it. It deletes that window in window dictionary, and it draws that window on the other side of the polyline rectangle, and then it puts that information inside the window dictionary. It's ID inside the dictionary, and a hole is made for that new window, whether it was in the original one or the original one was erased and a new one was created. And that window dictionary is added to the window dictionary. And the new the ID of that dictionary is returned. And let's see. Then here's the actual function that draws the window. I think. Oh no. This is a draw window from rect function. And what it does is it takes that uh, rectangular polyline, the wall entity that it's on, the wall thickness, and the handedness. That means it's just a 1 or a -1, which will indicate what side of the uh, polyline to draw that window on. Because it could be, depending on how it's drawn, it could be on either side of the uh, polyline rectangle. And what can I say? Let's see. First, it gets the points from that polyline, as explained before, up to here. Now it's got the individual rectangle, the individual points of the rectangle, and then it sets the first point as the window origin point, and then the second point to the point that defines um, the x-axis of that Windows coordinate system, and then the fourth point here is the y vector of that Windows coordinate system. It ignores the third because that's just the opposite corner, and that can be implied. And then what it does is it subtracts those points from the window origin to get the x vector and y vector, and then figures out what the length is, and it creates these unit vectors by calling the unit vector function. So now you got the x unit vector, the y unit vector, the z unit vector. And with the origin point and the wall thickness, which is passed as a as a as a parameter, and as is the wall entity, and as is the handedness. So then the draw window function is called, and that's the function that actually draws the window. And here it is with all those parameters that are called. And the first thing it does is it makes sure that it goes back to the world coordinate system. And then it goes to the user coordinate system defined by the Windows dictionary, by the parameters that are passed to it. Then it goes to the origin of the frame here. And it gets to the origin of the frame. It changes to the window frame layer. It creates a box. And then what happens through this here, it moves the origin and it draws another box, which is like the inside of the frame, which has to be subtracted from the outside of the frame. And so that gives you, when you take a box away from a box, that's what gives the frame. And then it moves to the origin of the glass pane, and layer is changed to the window glass layer. And the box command is called, and then the window is drawn. At this point, what happens is it goes back 5 coordinate systems to get back to the original coordinate system, and then all it has to do now is create the window dictionary. So it creates a blank dictionary like that, and it creates the window coordinate system. I'm not even sure if this is used anymore. I don't think so. Oh yeah, yeah it is. Yes it is. And that is basically the transform matrix of that window coordinate system, like I explained in the previous video on transform matrices. Here's the window origin point. Here's the x-axis vector, the y-axis vector, the z-axis vector, and then you got this 0001 on the bottom. And so now that it has all this information together, it puts all the information into the window dictionary and it returns the window dictionary. And those are the main functions of this program. Here's a function that gets the window dictionary, and it does that by finding it on the named object dictionary, which is a dictionary which always exists in an AutoCAD drawing and is made to put attach other dictionaries so that they can be found easily. And its key is just window dictionary. And what's this? Oh, this is what happens if that dictionary does not exist. It just creates one. Creates a new window dictionary. And it puts it onto the named object dictionary here with the dictadd function. And this here is called when this file is loaded. And just says if the window dictionary is not loaded, it loads the window dictionary. Oh, here's the adjust window function. And basically what it does is it figures out, it's past the window dictionary and the point, and this point redefines the nearest window corner. It knows what the window is. It can figure out which window corner is closest, and then it updates the window dictionary, and it or the information rather, window information, and it just calls the window draw window function again. And over here, it's figuring out which window corner change. Is it the origin? Is it the point that defines the delta x? Is it the point that is the opposite corner of the origin? Or is it the point that defines the y-axis? Once it's figured that out, it adjusts the data accordingly, and then it calls the draw window function using that modified data. And the draw window function returns a new window dictionary. Let's see. Here's some smaller function. This gets the corner points of a window given its window coordinate system, the length along the x, the length along the y, and that will return a list of points that the window corner points. Here's the function that seals the window, uh, the hole that a window is in, and it does it by getting all the necessary information out of the window dictionary that's passed to it, and then it creates a user coordinate system matching the Windows coordinate system, and it just draws a box from the origin using the length, the x length, the y length, and the wall thickness. And then it's unioned. That box is unioned with the wall, and that seals the wall. And then the previous um, user coordinate system is returned to. And this just does the exact opposite. It makes a hole for a window using a window dictionary, and it just does the exact opposite as this right here. As a matter of fact, the only thing that's different is the last line. A subtract instead of a union command is executed. And here's the delete window and window dictionary function given a window dictionary. Figures out what the uh, entity that is the window frame and the entity as the window glass, and it erases them both. And then if the seal hole option is true, it seals the window hole with the previously described function. It finds out what the dictionary ID is from the dictionary, and it removes its own dictionary from the window dictionary. Here's the isEntity part of a window function. It's basically the same function as that spatial conflict solid function. That's the function that determines if two 3D solids have an intersection. Here's the set UCS to window CS function. I was late. I better go to sleep soon. My girlfriend is not happy. Oh. You know what? I think that's pretty much everything important. I'm gonna go to sleep now. Mi novia probablemente es muy enojado a mí. Es 10:30. Siempre voy a ir a dormir. Gracias por aguantarme. Okay, well, ladies and gentlemen, for those of you who really wanted to understand the program, there you go. If you're even a slightly experienced Autolist programmer, this should give you a very good uh, tool to have a more advanced understanding of Autolisp, especially with dictionaries and uh, entity coordinate systems and matrix math, making a non-trivial program in Autolisp. It's been my pleasure to write this program for you and to create these videos. My next video is going to be on how I rewrote this program in Visual C#.net. Why do you think I did that first video on how to create a project in Visual Studio.net for AutoCAD? That's why I did. So in any case, look for that pretty darn soon in the future. I've already written the program. Now all I got to do is create the video. So please, if you stayed this long and you enjoyed this, give this video a thumbs up. And of course, what's that other thing you can do? You can subscribe to my channel. Maybe write a nice encouraging uh, comment. Tell me what you might want me to do next. I haven't completely decided next, aside from what I told you. Other than that, have a wonderful night, and I'll see you next time.